Hi, fellow geochemists and geochemistry enthusiasts. Welcome to Geochemist Tea, the only podcast for people who love geochemistry with a side of tea. Our mission is to inspire aspiring geochemists and to introduce our listeners to niche geochemistry topics. I'm your host, Sam Scher, and this month we're talking with Britt Bluemel about how, while different in terminology, the interpretation of geochemical data and machine learning are more closely related than you may think. Britt Bluemel is the Global Business Development Manager for ALS Gold Spot Discoveries. Britt, welcome to Geochemistry.
Hey, Sam. Thanks for having me on the podcast. I'm so excited to be here.
You're welcome, and thanks for coming. After graduating with her Bachelor of Science from the University of Victoria in Canada with a degree in Earth and Ocean Science, Britt worked as a geochemist for Barrick before heading back to do a master's at the MDRU at UBC in geochemistry. After graduating, Britt worked for the now geochemistry infamous IO Global, where she worked as a geochemist with other geochemistry friends of the show. Moving on from Index, she then met me working at CoreScan before finally ending up at ALS Gold Spot Discoveries. So, Britt, within that brief bio, I'm sure our crew would love to hear more about your journey through education and the mining industry.
That was such a very excellent introduction, Sam. Thank you for that. And I was devastated to miss the geochemistry special, a very IO Christmas that you had
Can I
just a couple months
say
ago.
that I have gotten an email from somebody who will remain nameless that was very upset and was like, "Do you even know her?" And I was like, "If you knew her, you would know why she wasn't there."
Oh my goodness.
Yeah.
Yeah. No, that's great. But I listened to the episode. It was really excellent. And I know you're working your way through the IO staff, alumnus even. IO
I would say
alums.
alumnus. Yeah.
Yeah.
Yeah. It was a
Yeah,
school
because
for
it doesn't
sure.
exist anymore. Which is
Yeah.
this came up in that podcast. That's a real loss to our industry that a group like that can travel around and teach training courses into mining companies. That's just not really available. And then so where does anyone learn their geochemistry these days? From the podcast.
From the podcast, talking with Jeff Bigelow, I guess it was January. Newmont has their own internal training program. So maybe if you're lucky enough to
Mm-hmm.
have that or have some mentors somewhere out there. Otherwise, you got to settle for the mentorship of geochemistry. Yeah. It's a great
In a
it's a
port
great
in
one,
a
but it's rough.
storm.
Yes.
Got to start somewhere.
Agreed.
So yeah, of course, I would love to share about my journey through the mining industry. I got into geochemistry really early in my bachelor's. I was really fascinated by it. And for those of you that don't know, UVic as a school has a really excellent earth and ocean science program, but it is by no means a hard rock geology program. So,
Mm.
like Carleton, for example, Queens, those are both universities that have excellent economic geology programs. But UVic did not. But it did make a whole bunch of very good earth scientists and very critical thinkers. But I was really interested in geochemistry from there. And so I did some work in geochem with IO, and then we got bought by Imdex. And then in 2017, I attended this conference called Exploration 17. It happens every 10 years. So there's one in 2007, 2017, and the next one will be in 2027. And I went to a presentation, the 10-year outlook presentation in geochemistry, which was delivered by a fellow named Paul Agnew. Paul Agnew at that time, and actually still, is the chief geologist for Rio
Rio.
Tinto.
Yeah.
But previously to that, he was the chief geochemist for Rio. And so he was giving this 10-year outlook geochemistry presentation, and he was talking about some things that we were currently doing at that time at Imdex. And then he mentioned a few things that he thought were on the horizon. One of those things was core scanning technology, specifically CoreScan. So I stood up out of that presentation and I marched over to the CoreScan booth. And I told them how great I thought they were and that I would like a job, please.
This sounds suspiciously similar to how you got a job, according to Dave Lowy at IO Global.
Oh, yeah, that's another really good one. So I marched over to the CoreScan booth and I told them that I would like a job, please. And they actually, at that time, very fortuitously, were looking to expand into North America. And I was living in North America at the time. And so that just worked out really well. And they said, sure, that's great. Dave, I think I managed to convince him to give me a job by making him drink coffee outside in January in Canadian winter. We were gonna just have a chat, and it was before I joined IO Global. And I said, "Oh, it's very noisy inside the Roundup conference," because we had met at Roundup back when it was at the Westin. And if anyone
Ooh.
remembers Roundup from when it was at the Westin, which is just down the street from where it is now, it was a smaller venue, and it was really great. It was a lot of a different feeling than it is these days. And my favorite part about the conference there is that at night, the party upstairs, the floor was carpeted, and the carpet would get so sticky. It was so full of beer. Anyways, I digress. So Dave and I met there, and I asked, would he like to go outside and we could sit on this bench and overlook the water? And it wasn't too cold, but it was January, and it is
In Dave's
Canada.
memory, it sounds very cold.
Yeah, no, he had just come from 40-degree weather in Perth. It was so, and he's just wearing like a regular suit jacket. And so we sat outside for probably half an hour. And then he was like, Britt, if I give you a job, can we go back inside? And I was like, oh, yeah, of course, let's go. Dave, what a hero.
Honestly, I feel like this is the inspiration that some of our young listeners need, that you can just go up to companies and say, I would like a job. And with that confidence, you could perhaps also become employed. I love that.
Yeah, I would like a job. At least you're being direct. And I would honestly also follow it up, knowing what I know now, with I would like a job, comma, and here's what I can do for you. Make it a little bit less selfish.
I'm not mad about it though. Oh my God.
No, no,
Uh,
but I guess in terms of like advice for listeners would be to follow your personal interests, like your personal passions. So recently we had this conversation with a few folks about going back to do your PhD after doing a master's and working in the industry for a while. Would you go back and do that? And in my opinion, it would have to be something that a person is really passionate about. And I think that's probably why I've transitioned my career around in the way that I have, because I'll get really interested in a specific topic like core scanning technology, core sensing technology, or data science and machine learning. And so I want to go and learn about that thing, and I'll just go and work for that company rather than go and do an applied master's or a PhD in that topic.
I think that's really helpful because I've definitely received a lot of, and I don't know how, I'm not necessarily, to our listeners, I am not like, I'm not the, I don't think I give some good advice, but I don't think I have the best advice for all things. But a lot of people will ask me to do this. Do you think should I get a PhD in it? And I think for me, I've done the opposite of you, where I've stumbled into opportunities, which has been great because I've learned a lot about them. So in my case as well, working for core scanning technologies, both in that and then adjacent to that, working in a lot of applied machine learning style stuff with those technologies, I feel like I've done many, at least masters and probably PhDs at this point, because it's not just learning so much about that technology, but also working on so many different deposits with all the different questions with it. So for me, I agree. It would have to be something really special to bring me into doing a PhD. But I think also there's so much that you can learn by just being in the right place. And maybe you stumble into it, or maybe you just demand a job. It could go either way.
Demand in a very Canadian, polite way. Do you think if you were going to go back and do a PhD, do you have an idea of what that might be for you?
Honestly, the closest I got to doing a PhD was to work with Peter Winterburn.
Totally.
Yeah, and
Yeah.
then
Yeah.
he left to go to Valley, and then also other things, but he was really pulling hard for me to do stuff. So for me, it was just
Mm-hmm.
having somebody that could just be that mentor to get me through and really teach me a lot more about a subject that I really love, which would be, to our listeners, applied geochemistry. Um, right now, I can't see who it would be that would really hook, line, and sinker bring me into a PhD. But right now, I just find working in industry so exciting that I don't know. I don't think I would want to take the time to do it. I don't know which who's giving more advice in this one. Oh my. All right. I want to thank you for all your advice that you just gave us, but now's time for my favorite segment, which is tea time. The kettle's hot, so time to spill.
Tea time. That's why we're all here.
Yes.
Really, let's be
Yes.
honest.
Exactly.
So the tea I decided was actually also an IO story. So
Ooh.
when you graduate from the IO School of Geochemistry, you also simultaneously graduate from the IO School of Drinking. And the advice that I would provide to anyone that chooses to step up and drink with some titans is always to choose Guinness, or if not Guinness, then at least a dark beer, like a stout, for example, because no one's ever going to tell you to chug a dark beer. Like, chug your Guinness, finish your Guinness. Never happened, never. Because if you're drinking like a gin and tonic or even a wine, you're like, okay, let's finish up our drinks and go to the next thing. And then you end up finishing a bunch of drinks and you're like, oh, that was too many. So if you think you might get outdrank, and this isn't just for geochemistry and geology, this applies to any real life scenario. If you think you might get outdrank, choose a dark beer. I feel like
So
this
what
is
was
also
your
very,
It's funny because we have heard this advice definitely during the IO special. So I
oh,
think
good.
anybody that's heard this advice can hear the context. But in what context did you learn this particularly?
I saw it happen perhaps the other way around, where some folks foolishly didn't choose to drink Guinness and they chose to match someone who we refer to as the wine monster so affectionately. Um, it's a cap worn with a lot of distinction and distinguished. So some people chose not to drink Guinness and they chose red wine instead, and it
They
went
drank.
poorly.
Yeah.
It went poorly.
Everybody drank 2 bottles that night. Okay.
Yeah, yeah,
Or
absolutely.
more.
That actually, it seems like drinking is the, excuse me, the segue about how I got into geology in the first place. I was at UVic doing this Earth and Ocean Science degree and looking around at all the different disciplines, physics, chemistry, math, biology. And I met the Earth and Ocean scientists and the folks in that program, and they liked to ski and they liked to play chess and they liked sports and they liked to drink beer. And I said, oh, you guys are great. Who are you? And they were like, oh, we're the geologists. And like, perfect. That, you guys, what is that? Geology? Okay, great. Good enough for me. Here we go.
Oh my. I feel like it always all starts out the same for us. Nobody
Hmm.
escapes it. Okay. So moving on from our talk of drinking and also more good unsolicited advice. For this episode, you provided us with an article about the application of random forest algorithms from the Journal of Geochemical Exploration, which is actually really cool. Usually we don't find these in our hometown journals, so I loved that. Anyway, it was entitled Using Machine Learning to Estimate a Key Missing Geochemical Variable in Mining Exploration, Application of the Random Forest Algorithm to Multi-Sensor Core Logging Data. And just like for everybody, as like a brief tease here, they weren't estimating gold or copper or anything. They were estimating sodium. Could you take us through the idea of this and the inspiration that you had when I first reached out to you to see if you were ready to be on the show?
Oh, yeah, absolutely. I chose this particular paper because it marries together two topics that I'm very passionate about these days. The first being geochemistry and the other being machine learning. And the thing I really liked about this particular paper is that it's very elegant. It's laid out in a very understandable way. It's very readable. And their goal is very relevant. Like you just mentioned, they weren't trying to do something like estimate gold. They were trying to do something like estimate sodium, which is going to guide and vector in the alteration space. And so this really scratches my brain in a nice way as a geochemist and an exploration geologist, because of course you will hear people say that the best pathfinder for gold is gold in some systems. It's a very common expression. But in many cases, gold does not have a big footprint. And so I'm driven by discovery and I'm an exploration geologist for sure at heart. And so any kinds of uh, workflows or tools that make a footprint larger are inherently very useful. So this particular paper, in looking for expanding that sodium footprint. And sodium is a very interesting element. We'll talk about that probably a bit later, because it's challenging to analyze.
You're not wrong. The way that this paper is laid out, everybody go and read this thing. It is, here is step 1, step 2, step 3 through I think 5 or 6. And it's just like, we want you to recreate what we've done because we think that this has value and will help other people. And I love that. I think all papers should be written like this. There should be no secrets. I agree.
Yeah, sometimes
Great
papers
call.
get really opaque and you're like, what variables did you really use? What transformations did you use? And yeah, it's all laid out really step by step like a recipe here. So that's great. But circling back to your question of our conversation when we were going to have this podcast and be on this episode, Sam and I were chatting about what would be a good idea to talk about and what the inspiration would be. And really it was how surprised I was when I joined a machine learning company, what machine learning actually is. Because as a geochemist coming into a machine learning company, I was very nervous. I was like, oh, I don't know anything about data science and machine learning. I'm going to join this group and I'm not going to know anything about what they're talking about. And it became immediately obvious right away that everything that the data scientist is doing in terms of workflow is very similar to what we do in the geochemistry space. You take similar sets of steps in a similar order. We just call them different things. So one of the backbones of this episode we're hoping is to demystify machine learning or data science or artificial intelligence for the geochemist and help you realize that you already have many of the tools that you need to move into the machine learning or data science space. You already have them if you're doing geochemistry. And so don't worry, come on in. The water's fine.
It's not too deep. It's not too cold. It's not too warm. It's perfect.
It's just
I
right.
agree. And that's why I'm building on that, starting off with, I love in all my Q&A sections to start off with explanations of terminology and really just things that if you're in this particular field, we tend to take for granted. Starting with the basic principles of ML would be great. So what is supervised versus unsupervised learning? What are some other common terms that we hear associated with them? For example, regression, classification, clustering.
Sure. Yeah, no problem. So if you go to Wikipedia or YouTube or wherever and you say, what is machine learning? You'll get basically these two buckets right off the bat. So machine learning is divided into two main fields, supervised and unsupervised. And there's another subfield within machine learning that can be either supervised or unsupervised, which is called deep learning. And deep learning is the processing of unstructured data like documents or images or text or something like that. We won't talk about deep learning too much in this particular episode, but large language models, for example, that's a type of AI that lives in the deep learning field. And anytime you see something with the word net, like a neural network or an artificial neural network, those live in the deep learning field as well. So if you think deep learning, you can think like image analysis, large language models, neural networks, that kind of thing. And neural networks are actually super old. They first came about I think it was 1943 or 44. That was the first time they were published. And that was a synergy between a biologist and a mathematician. Those two folks wrote a paper together in 1943, I'm pretty sure. And then it comes in and out of vogue, these neural networks, every 20 years or so. Right now, people are excited about neural networks. So even though I said I wasn't going to talk about deep learning at all, we just talked about it.
I love it. It's the information that we need.
We'll go back up to the top. So we have supervised and unsupervised in terms of machine learning. And supervised learning is the use of a discrimination function based on prior observations to apply labels to incoming or unknown data. And unsupervised learning is about finding groupings of data in higher dimensionality space with limited preconceptions or limited knowledge of how those data points are arranged. And so you can think about supervised being a knowledge-driven approach and unsupervised being a data-driven approach. So supervised, for example, is classification, like you mentioned, and classification for our geologists is like a QAP diagram, for example. So we can discriminate granite from syenite based on the quartz content. There's also regression in terms of our supervised options. So this basically just classification or regression. And in regression, we're trying to predict a variable, for example, like the revenue of ice cream sales based on some kind of influencing variable like ambient air temperature. So if you wanted to see how much money you would make off of ice cream sales, you could just plot the changing air temperature and you could predict with a regression model your ice cream sale revenue. And then in unsupervised, there's a few different flavors. So we have clustering and anomaly detection and association mining, which is like a market basket analysis. So based on what's in your basket at the supermarket, can we predict what other items will go in your basket? So if you have pasta noodles, then a highly correlated item to go into your basket might be pasta sauce or something like that. And then another, probably aside from clustering, the most common thing that people use in the unsupervised field is dimensionality reduction. And so for the geochemist, they'll know, very familiar with the principal components analysis. It's super, super common. But there's also TSNE, which is T stochastic neighbor embedding dimensionality reduction, or UMAP, which is a more up-to-date version.
So you talked a little bit about this, having now introduced us to these common machine learning terms. Then you alluded to it with the PCA, but I guess they're really not so dissimilar to common techniques that we use as applied geochemists.
Totally. Yeah,
Totally.
exactly. Yeah, nailed
There
it.
you go. Love that. Then we talked a little bit about this too, but usually when we hear about regressions being applied, people are trying to predict, say, gold grades or other things that are flashy like this, things that we need to know from like a almost like a monetary value point of view. But in this paper, it was so interesting. Could you present what the authors did and really speak to how novel to a data scientist would this be? But for a geochemist, on the other hand, it's solving a rather large and important problem.
Yeah, absolutely. So what they did that was really great here was predict sodium, and they predicted sodium using some XRF values to start with and some lithogeochemical values from, I believe, 260 samples. They had high quality, high resolution wet chemistry data, and then they had another data set in between the two to connect the dots. And so the sodium part is really interesting because sodium is challenging to analyze in wet chemistry, period. But it's basically not possible to analyze sodium from a PXRF because it's too light of an element. So you don't get enough signal returned back to the instrument to have enough counts for it to register. Sodium, you could analyze with a handheld device like a LIBS. You could use a laser induced breakdown spectroscopy unit, which actually I just learned that LIBS is like the colloquial term that we all use, but technically it should be called laser ablation atomic emission spectroscopy. So LA-AES, which is not as
Oh,
sexy a term.
no,
LAES. No.
no.
Of course everyone's calling
Liaise.
it LIBS.
Yeah.
LAES.
Liaise.
Yeah, I just learned that recently, so I thought that was really interesting.
Weird.
But the breakdown spectroscopy piece, it's called that because of the sound. There's actually a physical sound that
Interesting.
happens when you use the LIBS instrument.
Who knew that we had so much
Um,
marketing in geochemistry?
Geochemists are the original marketers? Never. Not at all. But in any case, so you could use, I digress, you could use lib quantitatively measure sodium if you wanted to use a handheld system, but you couldn't use XRF. So I thought that what these folks did in terms of being able to leverage other data sets together while using a data set like XRF, which is really fast and a great field tool, was really elegant, like I mentioned before, and really a very useful piece of data because not only can you use sodium for your vectoring, you can also use sodium for your alteration modeling, and you can use sodium within your lithogeochemical model. It's a really useful element that I don't think gets enough attention. And it's a really great one to use in this particular environment because you often have this albite kind of preconditioning of the rocks that will make them more brittle, and then that rheological change or contrast within the rock will often focus the placement of the quartz veins separately if you're looking for a gold system in this kind of environment because it's more fracturable because of this albite preconditioning.
Such a good point. Yeah. I was just watching you and I was just like, what's the next question? Anyway, I was just like, oh my goodness. We're talking about structure too.
Everyone's all starstruck. I'm starstruck because I'm so happy to be on geochemistry episode 24.
24.
24 is the best one. It's a nice round
24 is the
number.
best one. This is, well, not only this is our, I don't know if it's this one or the next one, but that's the start of our third year of being
Oh,
a
damn.
podcast. I know, fancy.
Oh,
Damn. Moving
Can
on,
we
though.
swear on this podcast?
We do whatever we want. I am not sponsored by nobody. Well, my own company sponsors us, and we say that minor swearing is fine. It always changes with whomever, I think is the word. Yeah, with whomever's on the
Whomever.
podcast. Yeah, when Dave was on the podcast, there was a lot of
Language.
colorful language that was used, but really everybody else has been very above board. It's surprising because I can just be terrible. But anyway, let's keep going because when Britt and I were first discussing this whole concept, which was to be like machine learning, not so different from what we do in applied geochemistry, and then she suggested this paper, and we were always not really going to talk so much about the paper, using it as a backbone to this talk, but I found myself going through it and just being like, well, we have to discuss section 3.2. So in section 3.2 of this paper, they talk about data exploration. And I will remind you guys here, this is a machine learning paper, but here they are talking about, and not that data scientists don't do all this stuff, but I just can't believe they're mentioning it. So here they're talking about data exploration. And if you have sat in any applied geochemistry course, all we do is talk about data exploration because that's what we do. So they're talking here about a lot of univariate statistics. They hardly even get into bivariate statistics, but basically, I'm thinking here, listening to this, that perhaps data scientists aren't so different from us as geochemists. They just perhaps don't know as much about the reasoning behind why you see certain elements there, as we were talking about the alibite, or what influence that they have towards figuring out different things going on in the future. So anyway, that said, I just thought that it would be interesting for people to hear really what, Britt, is your workflow as a geochemist like these data scientists in this paper? Do you start with univariate statistics, and from there, where do you go?
What a great question. So the workflow question, it's almost always the same, but like the secret sauce, I'll say, is in the data transformations and the selection of variables. And you can nest your workflow. So do, let's say the same one again in a smaller portion of data or a subset of data within the broader workflow to piece out or compartmentalize out sections or subsets of your data. But for the most part, it's the same nuts and bolts, and then you can add color with your transformations and your input variables. And so you start with your data cleaning, and then you'll do your scaling and your transformations, and then you could do your dimensionality reduction, and then you would create some kind of model, whether that's maybe you create a classification diagram, or maybe you create a random forest model, and you evaluate your results, and then you deploy your model on new incoming data. So it's clean, scale and transform, dimensionality reduction, create model, deploy model, create model, evaluate model, deploy model.
I like that. Yeah. Must evaluate.
Don't forget to evaluate your model. And that's very important for the people that are getting into machine learning and data science to think about that model metric and that model evaluation, because that's one of the places where data scientists and people that specialize in machine learning are actually quite different from the geologist, because in geology, we're very accustomed to having imbalanced data sets. That's just the world we live in. We're looking for ore deposits. Our data sets are naturally imbalanced. And so much so that we are very comfortable in that space. And the workflows that we generate in geology or geochemistry have this imbalanced bias almost baked in, versus the data scientist is very used to getting more balanced data sets. And so they'll work on a few different, whether it's oversampling or undersampling, those different techniques to try and balance their data sets, certainly. And so we're very good, geochemists and geologists, we're very good at dealing with imbalanced data just inherently. But I would say that the advice here, unsolicited advice, is when you're evaluating your model, be very careful that your model doesn't score 100%. If your model scores 100% or your accuracy is 0.1, your model is whack. This is the most colorful language I'm comfortable using. Or your model is frogged.
Okay. You can frogs.
It's fucked. If you score a 1, your model has a big problem, because that means that your model is overfit. And that means that your model is not going to be flexible when you incorporate new data or data that it hasn't seen before. So it's been overtrained and is overfit. And that's very common when you have imbalanced data to train your model. And so there's a couple of different ways around this imbalancing. You can oversample your data, like I mentioned, but you want to make sure that you do your cross-fold validation, like your k-fold validation or something, before you oversample the data. Otherwise, you're going to be overfitting the model to these artificially bootstrapped results. But I digress. So when you're evaluating your model, make sure it doesn't score perfectly, because if it scores perfectly, then that's overfit, and overfit is a no.
I love that. But I would also pick up on something that you said before, and I think one of the most important parts about being a geochemist and just having seen lots of data sets, having talked to a lot of people, been mentored by a lot of people, is just that you start to realize that the biggest thing that you offer is your secret sauce, which is just that you just have such a knowledge of, okay, we're in this type of system. This is what we're looking at. Oh, this element isn't working here. Oh, it's probably not working because of this reason or that reason. And you just have a really good understanding of what your elements mean in context of your geology. And it's just impossible to even impart this in 5-day learning session or something like that. It's just something that just takes a lot of time for you just to even keep remembering, or just to be able to put together all the pieces. And I would say to anybody listening to this, don't be upset that you're a year one geochemist working for a company and you feel, oh my God, like, how can I ever be as great as the greats that are out there in the industry? Anybody that's been on the geochemistry podcast. And the only thing that I would say to that is that it's just time. And that's really what's going to do it. Time, reading, listening to people, and just harassing people in general.
Yeah, and there's a couple, thinking about that secret sauce, there's a couple of easy tips and tricks that can be really helpful. So as you get to know different mineralization systems, you'll get a feeling for what elements are typically important in those systems. Or if you're trying to answer a certain question like alteration, you'll know what types of elements to include in an alteration workflow. And some of those elements may be tricky, like sodium is tricky to analyze for, but you can always fall back on element substitution. So for example, rubidium substitutes very nicely into the potassium site in white micas, for example. And so you can use rubidium in place of potassium if you happen to have poor quality potassium data for some reason. So getting, I would say, a piece of, again, unsolicited advice.
That's what we're here for.
Getting really familiar with element substitutions will be very helpful as you go through your career, and realize that sometimes you don't get all of the elements that you'd really like, but maybe you can use proxies. Proxies are very powerful in data sets that are maybe incomplete, and all data sets are incomplete, really. And one reference that the late and the great Peter Winterburn often recommended was a poster called the Earth Scientist Periodic Table of the elements and their ions. I'm looking at it, it's on my wall. But it's, yeah, you can get it on the internet, and it's an Earth Scientist's periodic table of the elements and their ions. And it takes the periodic table and it breaks it up and then duplicates sections and then draws these lines of ionic radius and charge. Have
It's
you
pretty
seen this?
wild.
Yeah,
Yeah.
it's great. And it's very useful if you want to say, okay, these elements behave together because they literally live in this, it's like a contour diagram across the periodic table that's been split out. And if you see the elements that sit together in the same contour lines, which are actually, they're not based on elevation, they're based on charge radius, you can see that they'll behave similarly. So it's very useful.
Yeah, I've given a few talks where one of them, I think I included this table in it, but also on this guy's website that put together this poster, he has gone into great detail on all of these things, and it's all free there for anybody's taking, and it's fascinating, and it's actually a really good point. I think that's great unsolicited advice, by the way. It's exactly what we needed. We've talked about transformations a little bit. There's many different ways that you can transform your data. In this paper, they talk about CLR, but I think it's important just why these transforms are, why we need to do them. So could you just take a hot second here and just explain to everybody why we use transformations.
Oh boy.
I know it's
Boy,
a deep
howdy.
pit.
Would I love to? You can't talk about geochemistry without talking about compositional data. So
No,
it would be irresponsible of us,
unethical almost.
unethical, certainly not to talk about compositional data. So at a high level summary, geochemical data is compositional data because it is forced to sum to a certain constant value, in many cases 100%, which means if you vary one of your input elements, the other elements that you're also measuring that are forced to sum to 100% will also vary. They will co-vary. And this is a problem because you can induce what's called a spurious correlation or a false correlation. And so if you look up compositional data, or closure is the term that's typically used in terms of geochemical data, because the data is closed, meaning it is not able to behave freely without influence from the other elements. And so a really easy way to get around this is to do some kind of ratio. Honestly, any kind of ratio will get you there. Any kind of ratio will open your data. It will, rather than being closed, then it will become open. So a very common and popular one is centered log ratio, but there's lots of other ones. There's the Pierce element ratio and the general element ratio. So, and you can use all kinds of different ratios. Anyone will get you there in terms of opening your data and then allowing it to vary freely in geochemical data space. And then which transformation you choose, which ratio you choose, is really going to be dictated by what input elements you've selected. And that is going to be dictated by your question. So if it's a lithogeochemical question, for example, you might choose a general element ratio, or an alteration question, you might choose a general element ratio or a Pierce element ratio. And that's really callback to the special sauce or the secret sauce of your input element. And that's going to circle back again to the most important part, is thinking about your question. What question am I asking of my data? Where am I trying to get to with this data? Because you could definitely open up a data set and just play around in there and see what elements are correlating with others once they've been opened and you've got around the problem of closure. And where you have different spatial associations, you can definitely get in there and let the data speak to you. And there's a lot of value there. But certainly it's important when you're looking at any type of data set to think, okay, what question am I trying to answer here? And even more so than that, is this data relevant or fit for purpose to answer the question that I'm trying to ask? In some cases, the data is not fit for purpose. And so there's lots of value and utility that can be extracted from that particular data set, but it might not be the right one to really answer the question you want. So for example, if you're trying to do a lithogeochemical analysis and you have aqua regia data and it doesn't have a complete digestion of your silicate phases, or even many of your phyllosilicate phases, then how could you possibly think that you could do a lithogeochemical interpretation there? Not possible. You could work around the back. I know that Juan Carlos Ordonez, who's been a guest on this podcast before, I've seen a presentation of his where he did some really nice work on a super large, the 30,000 samples or something, aqua regia data set. And the way that he attacked that problem was to do some clustering and work backwards from a not so fit for purpose data set towards an answer that they were looking for, which was rock type in that example.
I had forgotten about that. I don't think I saw that presentation, but I think he made that into a paper.
Maybe. I don't remember.
Maybe. Yeah. That's a good. We'll have to ask him. And something that I was thinking about as you were talking, there's more out there than just, say, the centered log ratio. I know it's not as in vogue. I know a lot more people use Python, but I use R on occasion. And there's a package, and they probably have it in Python as well. It's called Best Transform. And that will go through and that will find per element or per mineral, whatever you have, what the best transform is. And it gives you some stats following that. So there you go, some more unsolicited advice.
We should retitle this episode from Head in the Cloud, Feet in the Data to 45 minutes of unsolicited advice.
Unreal, unreal. Oh my goodness. Okay. We've been talking a little bit about lithogeochem, and something that I just wanted to ask that I think all of our listeners now are probably just dying to know about. We've talked a lot about machine learning. I think they're dying to know about this because I am too. Before all the time you spent here at Goldspot, how would you have attacked a problem like this? So applying learnings from lithogeochem data to this PXRF data set. So now we don't have random forest or anything to do this because not that it hadn't been invented yet, but it wasn't really in the geosciences yet, I would argue. So how would you have done something like this?
That's a great question. Dying to know.
Dying.
So
I'm absolutely dying.
conventional lithogeochem interp with the special add-on of predicting other variables with some connector variables in the middle. So conventional lithogeochem interp, we'd start with some biplots of our immobile elements like titanium and zirconium, maybe niobium over hafnium, and then I would have done some clustering. So from there, I would start data-driven. See where I have some groupings of samples that sit together naturally in immobile element space. And then I probably would have gone forward to make a custom classification diagram using something like a discriminant projection analysis. Now, discriminant projection analysis, that's a supervised technique. And that's where you have some well-classified, well-documented samples, well-labeled samples, which have known labels. And then you were going to calculate some new variables that best describe those rock types or describe those labels. And then when we calculate those new variables, we're going to try and maximize their between group distance and minimize their within group distance. And then we bundle this up into some kind of classification diagram. And then we would write from there, create a new classification diagram that includes the elements that we were missing and then plot them over there. But what we could do on the machine learning side to move it a bit further and to make it even more elegant would be to use something like a tree-based diagram like the authors of this paper did. And a random forest is really, it's a really excellent algorithm. It's a really excellent model to create for geological problems, geochemical problems. It's hierarchical, and geological data is hierarchical as well by nature. And so they tend to work really well, random forests.
I love it. Very cool. To round all this out, is there any kind of reference or when we were chatting in our little WhatsApp chat, any kind of Rosetta Stone for geochemist? Geochemist. I'll have to think about whether I want to cut that out. Like do some editing. Is there any kind of Rosetta Stone for geochemists interested in machine learning?
That's a great question. The references that I use the most, I think, would be towards data science. There's a website there that's very full, and scikit-learn, SCIKIT, scikit-learn, is another website that's just full of awesome references, very complete, very comprehensive. But probably my favorite reference, and this is as applicable for geochemistry stuff because it deals with multivariate data analysis as it is for machine learning stuff, is a YouTube channel called StatQuest.
I'm going right now.
Get on there. It's with a guy named Josh Starmer. He's from the University of Michigan, maybe. Josh Starmer, StatQuest is incredible. It's so good. He sings little songs about the
You would love this.
statistical
Okay.
method that he's about. He writes and sings little songs.
This is unreal.
And making it sound reductive. They're not little songs. They're incredible masterpieces of multivariate data analysis and statistics. And he explains really complicated topics in a very useful, understandable, and approachable way. StatQuest.
As a song.
Josh Starmer. They're just a small segment of song in the beginning for the introduction, and then the rest of it is just him speaking normally. I don't want you to think that you're about to get a full PCA clearly explained. And that's the other thing. He says clearly explained for everyone. They're great. Definitely go and check out
I love that.
StatQuest with Josh Starmer. I hope that he sees his listener or his views just skyrocket. February 16th, 2024. What happened? How did I become so wildly popular? Josh, if you're listening to this podcast, I appreciate you. Thank you for all your hard work.
Oh my God.
You don't know me. I'm a fan.
But one day he might.
He
One day
might.
soon. Yeah. Oh
God.
my
I can
goodness.
only dream. I'm fangirling over here.
I can see it.
Josh
To all
Starmer,
those that aren't seeing this, Britt is currently fanning herself. And
literally
she's red.
fanning.
Yeah, she's fanning herself. She's turned red. Yeah, fangirl. Okay.
I'm just blushing. Stats do it for me.
Everybody's got their thing. Oh my God. Well, look, thanks so much for being here, Britt. And I hope that this discussion has helped to further close this gap between applied geochemistry interpretation with machine learning. And I want to thank everyone for listening to Geochemistry. And again, a big thanks to Britt Bluemel for being on the show, dishing some tea, and taking us on this journey. Thanks to our sponsor, LKI Consulting, and to It's Water and Coma Media for our music. And I'm looking forward to chatting with everyone next month.
Great to be here, Sam. Thank you so much for the invitation. It was a real pleasure.